The red line shows the site of the new bridge over the Parramatta River. This bridge, when completed, will form part of the new Expressway to serve the northwestern and northern suburbs. The Expressway will extend across Tarban Creek and over the Lane Cove River. The new bridge is being built a quarter-mile downriver from the old bridge. The old Gladesville Bridge across the Parramatta River carried the traffic of Sydney's northwest suburbs. In part of the 19th century, this bridge was an engineer's pride. The opening span was operated by heavy gears and wheels. The traffic of the 1960s just could not be handled by the bridge that had operated for so long. The two narrow lanes were inadequate for modern needs. A new and wider bridge was called for. Upriver from the bridge is Sydney's largest gasworks. Colliers pass up and down the river bearing their burden from the northern coalfields. They pass through the open swing span and the old bridge and road traffic comes to a standstill. When this happens in peak hours, as it sometimes does because of the vagaries of the tide, the build-up of traffic on either side of the bridge causes delays, confusion, and frustrations. The span closes again and permits road traffic to slowly return to normal. The new bridge will have an arch of concrete rising high above the water to give ample clearance for the biggest river vessel. 6 lanes for road traffic are planned, and the bridge will have a single concrete arch 1,000 feet long spanning the river. Surveys and preparatory borings were made on each riverbank. The first work to be carried out is the excavation for the giant thrust blocks which will carry the concrete arch. Steel cofferdams to keep back the river water have to be built on the shoreline on either side of the river, in which this excavation can be carried out. The excavation is commenced to reach solid rock foundations on which the arch thrust blocks will be built. Steel sheet piles are driven to the rock below the riverbed. The cofferdam seals off the area to be excavated and the water is pumped out. Clamshell buckets dig out mud and silt from the riverbed inside the cofferdam so that the rock can be exposed and the foundations of the arch commenced. A trench is cut into the rock round the perimeter of the thrust block to define the excavation. Work proceeds on both sides of the river. A power shovel is lowered into the hole in the riverbank to enable the excavation to continue at a lower level. Testing is carried out on the sandstone rock. The bottom of the excavation is 40 feet below the surface of the river. Water is kept out by the steel cofferdam. Steadily, the drilling and blasting of sandstone rock proceeds. Next comes the concrete for the arch thrust blocks. Thousands of yards of concrete, carefully proportioned and thoroughly mixed, are discharged from ready-mixed trucks to hoppers and lowered down into the prepared excavations. The concrete is packed and consolidated with pneumatic vibrators. The arch thrust blocks take shape and form. Formwork is removed from a finished arch thrust block. At either end of the bridge approaches, concrete retaining walls form the ends or abutments of the bridge. Construction of the abutment now begins. Reinforcing steel is positioned around which the concrete is placed. The approach spans to the main arch are carried on long, slender concrete piers. The bases for these piers are formed up for concreting, the steel reinforcement added, and again concrete placed. The pier columns of the approach spans rise from their foundations. These columns are vertically pre-stressed with steel. The stressing bars for the columns are wound with special tape to prevent bond with the concrete. When the concrete in the piers is strong enough, the vertical bars are stressed. The required stressing load is applied with a jack and the stressing nuts tightened down. With the pier columns completed, a cage of steel reinforcement for the headstock is fabricated on the ground. The cage is then lifted into position. Concreting of the headstock follows. The concrete is hoisted into position and discharged into the headstock formwork. In the meantime, on the southern shore, a casting yard has been set up for the manufacture of the pre-stressed concrete deck beams. These beams, 100 feet in length, weigh about 65 tons. The reinforcement is placed in position and the ducts for carrying the pre-stressing wires are also placed. Pre-stressing cables are inserted in the previously placed tubes. Concrete for the deck beams is mixed in a pan mixer set up nearby and dumped into motorized skips traveling on a monorail system between the mixer and the beam forms. The concrete in the beam forms is packed and consolidated with external mechanical vibrators and also with internal pneumatic vibrators used by the concrete packers. The top of the beam is leveled. After the concrete reaches the designed strength, stressing jacks are applied at both ends of the beams. The necessary extension of the pre-stressing cable is checked and recorded. Stressing the beam causes it to hog or lift off its bed. The length of the beam is carefully checked and recorded. The finished deck beams will be placed in a position using a steel launching truss. The truss itself must first be launched from the abutment to the headstock of the first pier. As the truss moves out from the abutment, it is held by mobile cranes. Gradually, the truss is winched out towards the headstock. The landward end of the truss is raised off the rails into position. The forward end of the truss is lifted and placed in position on the rails already set on the top of the headstock, and the truss is ready to take the first deck beam. Progress is obvious, as seen from the air. The deck beam is moved into position along the launching truss. The beam travels along the truss and the forward end reaches the headstock. The truss carrying its beam is winched sideways until the beam is in the correct position. The beam is then lowered, one end on the abutment and the other on the pier headstock. Meanwhile, work has been going on in the river. Foundations for false work to carry the arch are being prepared. Before the concrete arch can be erected, a temporary steel structure known as false work must be built to carry it. Initially, tubular steel piles will be driven to the rock below the riverbed. Tubular steel columns will be placed on these piles. The tubular steel piles are cut and welded. The foundation piles are driven to rock below the riverbed. A floating pile rig does the job. A diver descends to check the condition of the steel tube piles. The tops of the piles are cut back to level and then prepared to take concrete caps. A steel packing piece is inserted in the top of the pile to hold the concrete cap. Timber formwork is erected around the top of the piles in preparation for placing the concrete. Ready-mixed concrete agitators on barges are used to bring concrete out from the shore. The unusual operation of placing concrete from waterborne agitators proceeds. The piles are now ready to take the steel false work which will carry the concrete arch. Tugs tow steel columns, which have been fabricated downriver, into position for erection on the pile caps. The false work erection is carried out by the Titan, Sydney's largest floating crane. The false work columns are attached to the crane's jib. And the columns are lifted from the water. They are gently placed on the pile caps and secured to previously set bolts. A total of 19 pairs of columns will be placed in position for carrying the steel falsework on which the concrete arch will be erected. With the columns in position, the steel girder spans, which have been assembled on shore, are now placed. The falsework girders join up and are bolted together. Whilst the bridge is being built, a shipping channel must be provided. A 200-foot opening is left through the falsework arch on the deepest part of the river towards the northern shore. No risk can be taken of collision between shipping and falsework. More columns go up, more girders are placed. Two steel trusses to span the shipping channel are built on shore. The first one is brought out by the Titan. The giant floating crane lifts the first 200-foot truss and maneuvers it into position. Ballast tanks on the ends of the truss are used for close adjustment of the truss's position. The second truss comes out. The second truss is safely launched. The temporary steel structure is now ready to take the concrete arch, shown here in diagrammatic form. Phase 1 of the construction is complete. The engineers look forward now to the next stage of the job, when plans are transformed into reality and the new traffic artery is ready to serve the community. The new bridge was designed by Maunsell and Partners of London. The design was checked by the Department of Main Roads in consultation with the Sydney University Civil Engineering Department and by the Fresnay Organisation of Paris. The construction is being carried out under contract by Stewart Brothers and Partner of Sydney.